In 1869, a Russian chemistry professor named Dmitry Mendeleev was writing a textbook for his students when he began to wonder how he could best explain to them the 63 elements that were known at the time. To help formulate his thoughts, he constructed a card for each element. On each card, he wrote the name of the element, its atomic weight, its typical properties, and its similarities to other elements. He then laid the cards out like a game of solitaire and began arranging them over and over, searching for patterns. Then came the moment of discovery. Before him was something extraordinary. The elements fell into 7 vertical groupings. Each periodic grouping had members that resembled one another, both chemically and physically. Mendeleev had discovered the periodic table of the elements, a map showing how all the elements related to one another. A map so precise that Mendeleev believed he could also use it to predict the existence and properties of 3 elements no one had yet discovered. One would be like boron, he said, one like aluminum, and one like silicon. Eventually, the elements were discovered, and Mendeleev was proven right.
There was actually a little bit of controversy because a German chemist named Lothar Meyer had come up with roughly the same idea. But Meyer didn't quite have as much courage. So that's actually an interesting thing. Here is this German who comes up with the same idea of periodicity, of which there were hints already before, but he doesn't make the predictions that Mendeleev does. So here we see the power of a risky prediction in having people accept a theory. There is nothing more powerful than making a prediction that's not obvious.
And then have it come true.
And have it come true. Mm. The periodic table is our icon. I mean, that's what we associate with chemistry. You go into any chemistry room, you see it.
Why is the periodic table of elements significant? It forever changed the way that everyone would learn and understand the elements. The periodic table of elements is to chemistry as notes of music are to a Beethoven sonata. In honor of Mendeleev, his name is now literally attached to the periodic table. The element 101 was named after him. It's called Mendelevium.
It's not only chemists who like the periodic table. I hear you carry one around.
I do carry one, yes, sir.
Show me.
You never know. And I seem to use it a lot.
Let's see.
It's a small one.
So I'm going to give you a test. What is under nitrogen in the periodic table?
Nitrogen is 7.
Yes.
I have to think a second.
Under
sulfur.
No, you're wrong.
Oh, God. That's
close.
Why I carry
You're one off. It's phosphorus.
Oh, phosphorus.
Phosphorus
15.
is right.
Phosphorus is 15?
Yeah, you have to add 8 at that point.
See, that's why I carry it. I can't remember. So it's 7 plus 8, 15 phosphorus. Okay. There's a pattern there. I get it now. At the turn of the 19th century, electricity was all the rage. People were busy making batteries and connecting them to just about anything to see the reaction. Electricity was like a new kind of fire. One of the great battery junkies of the day was Humphrey Davy, a self-taught English chemist. In 1807, Davy was performing a battery experiment in his lab. He melted some potash, a mineral found in the ground that also forms in the ashes of wood. Chemists had speculated that potash was a compound of several elements, but had not been able to prove it. Davy wanted to see if electricity might provide the answer. He ran some wires from one of his biggest batteries to the melted potash. Pure potassium began to emerge. Davy had discovered the power of electricity to react with chemicals and transform them. Eventually, electrochemistry led to the rise of the aluminum industry, the production of semiconductors, solar panels, LED displays, even rechargeable lithium batteries. In the 1850s, Robert Bunsen and his research collaborator Gustav Kirchhoff conducted a series of experiments to determine why substances emitted specific colors when placed in a flame. The color they determined indicates what elements are present in the substance. For example, if sodium is placed in a flame, they observe shades of yellow. Copper, shades of green. Strontium, shades of red. That was a good one. While watching the experiments, Kirchhoff was reminded of how a prism spreads light into a rainbow of colors. So, using a prism and the pieces of a small telescope, Bunsen and Kirchhoff built the first spectroscope, an analytical device they'd hoped would help them see the spectra coming from heated substances. And it worked. As an element was put into the flame of a Bunsen burner, the light from the heated substance passed through the prism of the spectroscope, where it then spread into a ribbon-like spectrum of colors, riddled with dark lines. The combinations of bright colors and dark lines were like barcodes, indicating what atoms were present. When burned, each element produced a completely unique spectrum. Using their spectroscope, Bunsen and Kirchhoff were able to discover two new elements, cesium and rubidium. One day, Bunsen and Kirchhoff decided to test their invention with sunlight. It produced a spectrum that featured two lines that were identical to those in the spectrum produced by sodium. Bunsen and Kirchhoff had discovered the presence of sodium in the sun, 93 million miles away. Suddenly, scientists had a tool to help them study the chemistry of the heavens.
Liftoff. We have liftoff.
Today, the legacy of this great discovery lives on in the exploration of space. A form of spectroscopy is being used to study the atmospheres of planets, to search for signs of water, signs of life. Our next great discovery is the story of Joseph Thomson and the electron.
Here we are.
So everything that we can see is made of chemicals.
That's right.
What's the future?
And they're all bonded through electron interactions.
Thank goodness.
And the future.
To find out about it, I paid a visit to Harvard University. Dudley Hirschbach is a professor here and winner of the 1986 Nobel Prize in Chemistry for his research into the dynamics of chemical elementary processes. So, Thomson didn't discover the electron.
Well, it's of course said that way, but he didn't discover in the sense that he said, Eureka, I've got this thing, here it is. He did an experiment that allowed him to measure the ratio of the charge, the electric charge, to the mass. And then later he was able to get a rough measurement of the charge and therefore show that the mass was very, very small. It was about 1/2000th of the mass of the lightest known atom, hydrogen atom. So it showed that he could extract in the experiment a very small piece of an atom. Well, that was a tremendous shock. People didn't imagine. Yes, yes. Electrical piece of an atom. It was a very small part of the atom.
At the time of his discovery, Thomson was a professor at England's University of Cambridge.